All right, so we are gonna tie up the urinary system, then kind of segue into water and pH balance, which are obviously very related, but pull into some of the other concepts we've been talking about up to this point. And then we'll get into the immune system. So let's do it. All right, so we've been talking all about the kidneys and the nephron. Just brief review. Talked about the glomerulus, where you had the blood coming in, the afferent arteriole, leaving the efferent arteriole. What was the process that was happening in the glomerulus here in this glomerular capsule or Bowman's capsule?
Filtration.
That was the filtration. That's where you are having, again, 180 liters of this filtrate being formed per day, of basically water and all sorts of small solutes leaving the blood, entering the renal tubule. And then what's going to have to happen next?
Resorption.
What's that? What happens after filtration?
Capillaries?
What about capillaries? I mean, the glomerulus is actually capillaries. Actually, where does this efferent arteriole go to? Where does it end up?
Is it reabsorbed or?
Yeah, but so what happens to the efferent arteriole? Where does it end up heading to next?
Peritubular capillaries.
Yeah, the peritubular capillaries, the capillaries that are then around the tubules. So that's how we can get tubular reabsorption, where you take most of the water and the solutes that you want to keep, the nutrients and stuff, and bring them back into the bloodstream. That was that tubular reabsorption. We talked about the lion's share of that is happening in this PCT, the proximal convoluted tubule. What is the other process that's happening as well?
Secretion.
Tubular secretion, where there's stuff that's still in the blood that you want to get rid of. In the PCT, you're actually secreting like hydrogen ions. We're going to see that's going to be an important part of pH balance. If your body is too acidic, you can just actively move hydrogen ions into the tubule, so your pee will be more acidic, but it'll balance your body's pH. Then we talked about the loop of Henle, the descending and ascending limb of the loop of Henle. What were the properties of the descending limb of the loop of Henle?
Permeable to water, but not to solute.
Yeah, exactly. Permeable to water, but not solute. And so as you get down, especially in these juxtamedullary nephrons, it's like 1200 milliosmolar outside here, super salty, which means as you go down, you're going to have osmosis, and more and more water is going to go back out of the tubule and back into your body. And what about in the ascending limb of the loop of Henle?
The opposite.
So impermeable to water, and what else? There's something a little more specific.
Isn't sodium getting pumped out?
It's actively pumping sodium, reclaiming sodium. So by the time we got up to the top of the ascending limb of the loop of Henle, the filtrate in here was really dilute, like about 100 milliosmolar, much less osmolar, much more dilute than your normal body fluids. Remember, that's how you're able to make dilute urine. If you want, you can actually pee out urine that's much closer to water than your normal body fluids. I mentioned that this is the DCT. The DCT does this little thing where it makes a relationship with the arterioles here. We're going to talk about that in more detail in just a moment, this juxtaglomerular apparatus. I have to spell it right. Juxtaglomerular. I'll write it out more pretty in a few moments. And then from the DCT, where do we head?
The collecting duct.
Exactly. The collecting duct is going to be the final place of adjusting the composition of what's ultimately going to be your urine. What were the two big things we talked about happening in the collecting duct as this filtrate is doing its final pass through the kidney's medulla and leaving into the ureter?
The aquaporin, let water out or reabsorb water.
And and what controls whether or not there's aquaporins or not?
Antidiuretic hormone.
Exactly. So if we have ADH, that hormone, which we've talked about, we'll talk about more, is coming from the pituitary gland. ADH inserts the aquaporins, and then the water is going to come back into your body because it's super salty out here. Yeah, if there's not ADH though, then this really dilute urine will continue to come out. So we'll have much more dilute urine, much lower specific gravity, closer to 1. If we have a lot of ADH, if we have a lot of aquaporins, we're sucking a lot of water back into the body, then the urine is going to be super concentrated because we're going to be pulling the water out and just leaving the solutes behind. Right? We're going to, that's part of that lab today. When your body is trying to conserve water, you're going to have more ADH, more aquaporins, much less ultimate urine volume because most of the water is pulling back into your body, much more concentrated urine because there's just the solutes and not as much fluid moving it along. What else did we talk about happening in the collecting duct?
Sodium getting pumped back out.
Say it one more time.
Sodium getting pumped back out.
What controls that?
The aldosterone.
Aldosterone. So aldosterone from the adrenal glands will tell the kidney tubule to pump more sodium back into the body, reabsorb more sodium. So again, that's going to be part of our lab today as well. If your body is trying to hold on to sodium, it's going to be having more of this aldosterone to keep the sodium in your body and not have it in your pee. If you have enough sodium in order to maintain sodium homeostasis, you might have to let more sodium leave your body. Now, this is in some of people in their hypotheses for the lab today use this word normal, which is not a very useful word when we're talking about kind of composition of urine. Like normal doesn't really mean anything. Your urine, what's normal depends what you've been eating or drinking, right? How much volume you pee out, how salty it's going to be, depends what your kidney has to do to maintain homeostasis. If you've been drinking a whole lot, you're going to pee out more volume because you have to let go of more water to maintain your water homeostasis, your water balance. If you've been eating a whole bunch of super salty stuff, you're going to pee out more salty be more salt in your urine because you're going to have to let go of more salt in order to maintain your electrolyte homeostasis. So normal doesn't really make sense. It's like, what's normal? Like, what's normal to, like, chase after your pet who's running away? It's like, it depends if your pet's a turtle or if it's a cheetah or something. It depends, it's going to be different depending on the different conditions. So that was what, in some of your comments, I'll talk about it more when we get to the lab. But the only thing you can really say with our lab hypotheses is kind of the relative volumes or amounts of salt between the different groups. Like, this group is going to have a more volume than this group because they drank more water than this group, and therefore they'll have to let go of more water than this group to maintain their water balance. So just kind of pH as well, right? I was talking about, we're going to talk about pH balance in a second. How much H plus you are secreting and putting in the tubule to eventually end up in your pee, it's going to depend on how acidic your body is from what kind of foods you've been eating and stuff. So how acidic or alkaline your urine is just going to depend on what your diet's been. So anyway, are there any questions about this kind of just big picture of what the kidneys and the nephrons are doing? Right, so if we're thinking about the volume, remember we talked about at the nephron, the very beginning, in this glomerulus, this filtration, we're making about 180 liters per day of filtrate. Crazy amount. You can't, you would dehydrate in minutes and be dead if that was your pee. So what's happening? You're reabsorbing. At any other place along the way, there's less volume. By the time we get to the very end, you've usually reabsorbed about 99% of that volume of that water. In terms of the osmolarity, it's a little trickier. Osmolarity at the end of the PCT was still the same, 300 milliosmolar. The bottom of the loop of Henle, it was down or up to like 1200 milliosmolar. At the top of the loop of Henle, it's down to 100 milliosmolar. What is the osmolarity of the filtrate at the very end of the collecting duct?
It really depends on what's in your body and what you need to pass out.
Exactly. It's going to totally depend. If your body is trying to conserve water, you'll have these aquaporins open, and it's going to be really salty. It's going to be close to 1200 milliosmolar. If your body is got plenty of water, it might be super dilute. It might be still close to 100 milliosmolar. So the osmolarity at the end of the collecting duct can be radically different depending on your body's needs and what it had to do to adjust to maintain water balance. So just making that clear. So any comments or clarifications for this? I realize I didn't put out a warm-up for this morning, so this is kind of your review for this material. Okay, before we leave the kidney, I do want to look at the juxtaglomerular apparatus in a little more detail. And you've already met it, right? It's the thing that's releasing renin that initiates the whole the whole renin-angiotensin mechanism. So juxta just means near, next to. Glomerular, near the glomerulus apparatus, ideally that does something. So these are going to be, in fact, let me just use my typing tool because it's going to be really fast, much faster to do this by typing. Especially modified cells of arterioles and distal convoluted tubule. That sense both blood pressure, right? The arterioles can sense blood pressure just by stretch, right? The more stretched out, the higher the pressure is inside. The less stretched out, the less the pressure is. And the distal convoluted tubule can sense the composition of the filtrate. Right, if things are going too fast through the tubule, there's not enough time to actually adjust everything like you need to. If things are going too slow, maybe you're pulling too much stuff out. Basically, this is going to be where you try to figure out whether the glomerular filtration rate is appropriate. So it's basically helps control that GFR, remember the glomerular filtration rate, by controlling blood pressure, basically. Right, so remember we talked about the glomerular filtration rate is ultimately being driven by the glomerular hydrostatic pressure. Right, that was ultimately what is driving the whole glomerular filtration. So if your glomerular filtration rate is dropping, what's the thing you're going to have to do?
Increase blood pressure.
Increase blood pressure. So one of the things this will do, if you are getting low in your glomerular filtration rate, if needs to release renin. This is going to increase blood pressure, which is going to increase the GFR. Right? This is the whole reason why the kidneys are in the kind of seat here controlling blood pressure. If your glomerular filtration rate is too slow, you need to increase your blood pressure in order to get the rate back up. There are other things that it can do as well. It can actually adjust the constriction or dilation of the arterioles. So it can constrict on the outgoing, like if we're looking at the afferent arteriole to the glomerulus, efferent arteriole. If things are too high, we can actually constrict here and slow things down. If it's too low, we can relax here and constrict here to increase more pressure inside the actual glomerulus to increase the amount of filtration, the amount of stuff that's leaking out. So in addition to adjusting your global blood pressure, the juxtaglomerular apparatus is also messing around with the diameter of the afferent and efferent arterioles to adjust the pressure in the glomerulus to adjust the filtration rate. So, but mostly, I just want you to think about the juxtaglomerular apparatus as these special cells here in the glomerulus, or actually in the afferent and efferent arterioles, as well as a bit of the kidney tubule that are monitoring pressure and composition of filtrate and therefore able to decide what it needs to do to adjust blood pressure in the glomerulus by either adjusting your global blood pressure with that renin-angiotensin mechanism, or also messing around with the diameters of the afferent and efferent arterioles. Should also mention that the juxtaglomerular apparatus, in addition to being controlled more locally by just these cells that are sensing the kidney function, it can be triggered by the sympathetic nervous system to release renin. Maybe I should add that in as well. So this, I'm trying, ANS, autonomic nervous system. So the juxtaglomerular apparatus is, mainly about controlling kidney function and glomerular filtration rate, but you can also have the sympathetic nervous system just kick it and say, release renin, we need to jump up our blood pressure right now, regardless of what the kidney's up to. So juxtaglomerular apparatus, also known as the JAGA, juxtaglomerular apparatus. Right, so for those of you that were already having trouble saying glomerulus, this will probably be even a nicer challenge that you can work on, juxtaglomerular apparatus. But eventually it will just roll off your tongue. All right, so questions about the juxtaglomerular apparatus? And again, you've already met it when we introduced the renin-angiotensin mechanism, because it's the thing that's releasing the renin. And now you get more insight into why renin is being released here, because blood pressure is what we are using to control glomerular filtration rate, which is at the core of your kidney function. It has to be approximately 100 to 125 mils per minute across all your nephrons for the appropriate processing to occur of the filtrate as you go through the tubules. Okay.